Much of the machinery used in industry is constantly in motion, and the moving parts in that machinery often roll or slide together at high speeds or under heavy loads. Under these conditions, the friction created by bare metal rubbing against bare metal would cause components such as these bearings to overheat and be destroyed. But normally, these machine parts won't actually touch each other. They're kept apart by a layer of oil or grease. If machine parts are kept properly lubricated, the equipment they're part of can run smoothly for years. Operators play a major role in keeping equipment properly lubricated. To help you do this, it's useful to understand some of the details about what lubricants are and what they do. To understand why lubricants are necessary, we first have to know what friction is. Let's look at an illustration that shows a microscopic view of two metal surfaces to see what happens when they're in contact. Under strong magnification, even the most polished metal surfaces appear jagged and rough with many peaks and valleys. The peaks of the two surfaces are in contact with each other. When equipment is started up, the jagged surfaces resist motion. This resistance to motion between two surfaces is called friction. Friction is also produced while the equipment is running, as the jagged surfaces and any small metal pieces that break off the surfaces scrape against each other. Microscopic scratches left from this scraping can eventually add up to severe wear. The purpose of lubricants is to make two surfaces slide against each other more smoothly, so a lubricant is a substance used to reduce friction. The lubricant separates the two surfaces and reduces the amount of contact between them. To be effective, the lubricant must be clean. If a lubricant contains dirt or other contaminating particles, these particles can bridge the gap created by the lubricant and scrape against the metal surfaces. This increases friction and will eventually result in wear. Oil is a liquid lubricant made from a synthetic substance or from petroleum. Oils made from petroleum are natural lubricants. Natural lubricants are the types most widely used in industry. One characteristic of oil is its viscosity. Viscosity is a measure of a liquid's resistance to flow and is an important consideration for determining the suitability of an oil for a particular application. A thin liquid, such as penetrating oil, has very low viscosity. There's very little resistance to flow, so it flows easily. A thick liquid, such as gear oil, has a high viscosity. It has a high resistance to flow. There are several different viscosity grading systems in use today. The SAE system, developed by the Society of Automotive Engineers, indicates oil viscosities with numbers referred to as weights. The higher the weight, the thicker the oil, and the higher the viscosity. In some cases, lubricating oils for industrial equipment are classified using the ISO viscosity grading system. ISO stands for International Standards Organization. As with the SAE system, the higher the ISO number, the higher the viscosity. Viscosity is greatly affected by temperature. An oil's viscosity, or thickness, increases as the temperature drops. The colder it gets, the thicker oil becomes and the less easily it flows. As the temperature rises, viscosity decreases. Oil gets thinner and flows more easily. So, the type of oil selected for a particular application depends on the temperature it's used in. In low temperature applications, lower viscosity oils are usually more suitable. They flow more easily at low temperatures and can reach moving parts better than thicker, high viscosity oils. In high temperatures, a thicker, high viscosity oil is usually needed. The oil has to be thick enough, that is, have a high enough viscosity to maintain a film over the moving parts it must protect. Many oils, of course, have to be able to lubricate in both low and high temperatures. For that reason, many oils today are multi-weight. They combine the properties of a lower viscosity oil for low temperatures with those of a higher viscosity oil for high temperatures. A common example is 10W40 oil. At higher temperatures, it will have the properties of a 40-weight oil, and at lower temperatures, it will have the properties of a 10-weight oil. The letter W follows the weight that's associated with lower temperatures. The fact that oil is available in many different viscosities makes it a good lubricant in a wide range of applications. In addition to providing lubrication, oil is also used for cooling machine parts. Fast-moving gears such as these can build up quite a bit of heat from friction caused by the teeth rubbing together. The oil picked up by the gears not only lubricates them, but also carries the heat away. Oil is also important as both a coolant and as a lubricant in bearings. These bearings support large, heavy rollers. The friction produced by the heavy load can build up a lot of heat in the bearings, but the lubricating oil flowing through helps keep them cool. Oil's ability to flow freely can make it unsuitable as a lubricant in some situations. In situations where a lubricant must stay put, a different type of lubricant, such as grease, is needed. Grease is usually the best choice in situations where a lubricant must stay in place. For example, grease's ability to stay in place makes it the best lubricant for exposed gears. There's no gearbox to hold a supply of lubricant, so the lubricant used must be able to stick to the teeth. This grease contains asphalt, which makes it thicker and better able to stick to gears and to equipment such as wire rope and chains. Although grease looks like it may be a thick, heavy oil, it's not. It's actually a mixture of oil and a thickener. The thickener is a substance that is similar in some ways to soap. The thickener soaks up the oil. You can sometimes see a small amount of oil separating from the thickener in grease that's been undisturbed for a long time. Many different types of thickeners are used in grease. One of the most widely used greases contains a lithium-based thickener. This is a cartridge of lithium grease for use in a grease gun. The letters MP mean multi-purpose. It's called that because lithium greases are both water-resistant and able to withstand high temperatures. So they can be used in applications where both heat and water are factors. Grease is made in several different grades or consistencies. Grease consistency is measured on a scale from 0 for very soft grease to 6 for very hard grease. In general, the more thickener in a grease, the harder it is. There are also extra soft 00 and 000 grades. This shaft, for example, turns a device that rotates through the hot gases produced in a boiler. The hot shaft turns in a sleeve bearing in this housing. The shaft and the bearing must be lubricated with a grease that will stay in place under high temperatures, like this hard grade 6 grease. A block of the hard grease is placed directly on the shaft through a hole in the housing and the bearing. The heat will cause the hard grease to melt, but only enough to lubricate the shaft without running out of the bearing. One type of solid lubricant is graphite. Graphite is a very slippery mineral form of carbon. Because it's not sticky, it doesn't attract dirt. It can also resist heat and pressure, which makes it a good lubricant for these heavy rollers. The rollers support a large rotating kiln. The high kiln temperature makes the rollers hot. This heat and the kiln's weight would quickly melt and wipe away ordinary grease. This graphite lubricant is in the form of a solid block. Because it's a solid, there's no danger of its melting away and leaving the metal surfaces unprotected. Tetrafluoroethylene is a solid lubricant that's a slippery plastic material. You've probably heard it called by its trade name, Teflon. Teflon can be formed into different shapes. For example, this is a simple sleeve bearing made of Teflon. And this is a Teflon sleeve bearing with a thrust face. Another common solid lubricant is a slippery substance known as molybdenum disulfide. MOS2 is its chemical formula. It's usually just called molysulfide. Molysulfide powder is typically blended with grease, in this case, lithium grease. Molysulfide powder is used because it has the ability to withstand extreme pressure. In this part, we'll take a look at some common additives to natural lubricants, as well as at synthetic lubricants. Additives are substances that are mixed with oils and greases to improve their lubricating abilities. A type of dried clay called bentonite is added to thicken the grease on the bearings in these rollers. Bentonite is far more heat resistant than some other grease thickeners. The rollers support a device that's used to clean the tubes inside an operating boiler. Heat from the boiler is transmitted to the rollers in the grease. Grease made with ordinary thickeners would melt and drip out of the bearings, but the bentonite resists high temperatures, so it keeps the grease from melting. Many substances that are added to lubricants are liquids rather than solids. Some of these additives reduce friction under conditions of extreme pressure, such as between gear teeth. As gears mesh together, the teeth rub against each other under great pressure. This severe rubbing can actually wipe away the protective lubricant and expose the bare metal. Gear oils usually contain chemicals called EP additives to protect metal surfaces against wear from rubbing. EP additives are used in greases or oils to form a protective coating on the exposed metal. The coating stays in place and prevents metal-to-metal contact, even if the lubricant is rubbed away. Lubricant containers usually have EP on the label if they contain an extreme pressure additive. Additives can also protect against corrosion due to contact with water. This bearing housing is constantly exposed to hot water vapor. Water works its way into the bearing and contaminates the grease. To keep the water from collecting in pockets in the grease and corroding the bearing, a water-stabilized grease is used. Although water and oil or grease normally don't mix well, an additive in the grease used in this bearing makes the water and grease mix thoroughly. This thorough mixing prevents the formation of water pockets that could corrode the bearing. Corrosion can also come from acids produced by lubricant oxidation. Oxidation occurs when a lubricant combines with oxygen, and it tends to occur more rapidly in equipment that operates at high temperatures. The acids produced by oxidation can corrode equipment and lead to lubricant leakage. Besides forming acids, lubricant oxidation can form harmful deposits on metal surfaces. The varnish deposits on this bearing came from oxidized grease. More severe oxidation produces carbon deposits. Both varnish and carbon deposits can greatly increase friction on bearings and other machine parts and keep them from operating freely. Carbon deposits can also collect in lubricants and form sludge. Sludge can clog lubricant pathways in machinery and keep the lubricant from getting to where it's needed. To help control oxidation, additives called oxidation inhibitors or antioxidants are blended with many lubricants. These additives greatly reduce the rate at which oxygen combines with lubricants. And to reduce the formation of carbon deposits in sludge, chemical additives called detergents and dispersants are added to many oils and greases. These additives keep particles in the lubricant suspended so that deposits in sludge don't form. Additives are able to make natural lubricants suitable for many different applications. But there are some extreme conditions where even additives aren't enough. For those conditions, many different types of synthetic lubricants have been developed. Synthetic lubricants are often made from substances found in petroleum and are designed to have the exact properties desired for specific operating conditions. One example of a synthetic lubricant is silicone grease. Silicone grease is highly resistant to oxidation. Synthetic lubricants can generally function in a wide range of temperatures. This synthetic oil is called a synthesized hydrocarbon, or SHC. It's able to continue flowing at very low temperatures and to resist oxidation at very high temperatures. This is a sleeve bearing. It's simply a round cylinder that supports a shaft rotating inside it. It's also called a journal bearing because the part of the shaft that rides inside the bearing is known as a journal. A journal normally rotates on a lubricating film of oil or grease. The lubricating film separates the journal from the bearing surface. This model has the housing and the bearing in two parts. Sleeve bearings are usually made of a very soft metal so that the bearing surface will wear before the journal. It's much easier and cheaper to replace a worn bearing than to replace an entire shaft. Both the shaft and the bearing will last longer when friction, which causes wear, is kept to a minimum. This special type of sleeve bearing is a bushing. A bushing is a thin-walled bearing that can be removed in one piece. The grooves in this bushing collect oil and help keep the shaft lubricated. Now let's look at an illustration to see how lubricant reduces friction between the bearing and journal. This is an end view of a sleeve bearing. Most wear on a sleeve bearing takes place when a shaft is starting up from rest. This is an end view of a sleeve bearing. Most wear on a sleeve bearing takes place when a shaft is starting up from rest. There is metal-to-metal contact between the bearing and the shaft journal at the bottom of the bearing. Most of the oil has been squeezed out from under the journal by the weight of the shaft. This gap is shown much larger than it really is, so you can better see how the bearing works. As the shaft begins to spin, it pulls oil underneath the journal. The oil forms a lubricating film that partially separates the metal surfaces. When a shaft is rotating slowly, such as during startup, a thin oil film only partially separates the journal and bearing surfaces. This means there is a certain amount of friction and wear. Normally, the amount of wear during startup is small and won't seriously affect a bearing's life. As the shaft speeds up, oil is pulled under the journal at a faster and faster rate. This builds up a thicker film of oil under the journal in the shape of a wedge. The oil wedge actually lifts the shaft up slightly and holds it away from the bearing surface. As long as the wedge of oil is there, there is little friction or wear between the two surfaces. That's basically how a lubricant works with this type of bearing. Rolling element bearings, sometimes called anti-friction bearings, use rolling elements to help reduce friction. The rolling elements can be balls, cylinders, barrel-shaped rollers, or tapered rollers. In most rolling element bearings, the rolling elements are held in place between an inner ring and an outer ring. A metal retainer or cage often holds the balls in position and keeps them from rubbing against each other. Many rolling element bearings have a metal shield on one side, or sometimes on both sides. The shield helps keep lubricant in and dirt out. These ball bearing rings have been cut in half to show their internal construction. The balls travel in grooves in the inner and outer rings. The grooves are called races. The outer ring of a rolling element bearing is fixed in a housing, and the inner ring fits tightly around a shaft. As a ball or roller rotates between the races, it draws a film of lubricant between it and the races. This film of lubricant separates the rolling element from the races. Bearing designs differ depending on the type of load they're designed to support. We're going to discuss the two types of loads that bearings can be subjected to: radial loads and thrust loads. Radial loads are forces that act along a radius of a bearing or shaft. This rolling element bearing is designed to resist a radial load. Thrust loads, or axial loads, are back and forth forces exerted on a bearing or shaft in a direction parallel to the axis of the shaft. Now take time to see some bearings designed to resist thrust loads by selecting Next. We've seen how rolling element bearings are designed and how lubricants reduce friction in rolling element bearings.